I am Aligar Lingappa, Associate Professor, Government First Kid College, Sandu. So today's my paper is Mechanics and Properties of Matter, Program BAC, Subject Physics, Semester per Semester, Session 6, Topic Elasticity. So today, now I will discuss about bending of beams. What is bending of beams? What is bending moment? What is the expression for bending moment? What are the factors on which bending moment depends? How the bending moment can be determined. So a beam is a rod or a bar of uniform cross section of a homogeneous isotropic elastic material whose length is very large compared to its thickness. So it is nothing but a bar or rod. So its cross section is homogeneous, that means uniform cross section. Isotropic elastic material, that means the same material. Its length is very large when it's compared to its thickness or say diameter. When a beam is fixed at one end and loaded at the other end, as shown in the above, that is below figure, within the elastic limit, it will bend and couple produce the inside it. So the upper surface of the beam gets stretched and becomes a convex shape, and the lower surface gets compressed and becomes a concave form. So bending of beams, here the one end of a beam is fixed to a rigid support, and the free end attached with load. Within the elastic limit, if it bends, the restoring couple which produced inside it at equilibrium condition. So what about the restoring couple produced? That must be equal to applied external couple. The upper surface of the beam gets stretched and becomes a convex shape, and the lower surface which gets compressed and becomes a concave form. So now you see this diagram where EF is a beam, its end E which is fixed to a rigid support, the free end F so is loaded as shown in the figure A. If it loaded, it bends down. The upper surface which uh, takes a form concave shape, and its lower surface is nothing but a convex shape. Now you see the diagram B. So when it bends, where one of the layer which neither compressed and nor elongated, such layer is called natural surface or neutral layer or neutral surface. What about the layers which are exist above that natural surface? All the gets elongated. What about the layers which are exist below the natural surface? They get compressed. So the axis passing through the natural surface or natural layer is known as natural axis or neutral axis. All the longitudinal filaments in its upper half are extended and those in lower half are compressed. The extension is a maximum in the uppermost filament, and the compression is a maximum in the lowermost filaments. That means lowermost layer surface. The amount of extension and compression decreases towards the axis of the beam, that means towards the natural surface or towards the neutral surface. So the filament EF neither extended nor compressed. This surface is called neutral surface or natural surface. The plane in which all filaments are bent to form circular arcs is called the plane of bending. So now what we saw in the diagram B, where plane ABCD is the plane of bending. The line perpendicular to the plane of bending is called axis of bending. The line EF is the natural axis or neutral axis. So now you come to the point of bending moment. What is bending moment? So what are the factors on which it depends? What is the expression for bending moment? Let us consider a beam, maybe a rectangular beam, ABCD. Its end AD, which is fixed to the rigid support, so called at point E. Another end BC is free end, which is loaded. When it loaded, which moves down, that means where the restoring couple which are produced inside the beam equal and opposite to that of the external couple. Where the EF that indicates the neutral surface, where the dotted curve that indicates neutral surface or natural surface, which neither elongated nor compressed, so-called neutral axis or neutral surface. What about the filaments or surfaces or the layers which are exist above that line EF? They gets elongated. Then what about the layers which are exist below the neutral surface? They get compressed, as shown in the figure A. Similarly, if suppose the load, if it is applied at both the ends, AD and BC, so now which forms like an arc of a circle. Here also where EF so-called neutral axis, neutral surface. What about the layers which are exist above the surface to get elongated? The layers which are exist below that surface so called compressed. All the layers they form like a arc of the circle. Let us consider a small part of the beam, say AB. Then let another layer, it is very near to that of the filament or neutral surface EF, so called at a distance Z. Where draw the radius from the points AB, A dash, B dash. It will, both the line they will meet at point O. That indicates, if suppose if you draw the imaginary circle where O be the center of the circle, where A dash, B dash and AB they are the arc of the circles. Theta, which is angle subtended by the radius vectors. Let a beam AB be fixed at A and loaded at B as shown in the figure A. EF is the neutral axis of the beam. Let us consider a section PBCP dash cut by a plane PP dash at right angles to the its length. An equal and opposite reactional force W must be acting vertically upward direction along PP dash. So look here, what about the W which indicates when PP dash, where the force which exerts vertically upward direction. The beam bend or rotate in clockwise direction. The couple produced in the beam due to the load applied to the free end of the beam is called the bending couple, and the moment of this couple is called bending moment. So we know that moment means it is a product of force and perpendicular distance. Let a small part of the beam bend in the form of a circular arc as shown in the figure B. This is subtending an angle theta at O. Let R be the radius of curvature of this part of the neutral axis. A dash B dash be the element at a distance z from the neutral axis. We are looking at R be the radius of curvature. Theta angle subtended A dash B dash arc of the axis which is at a distance from the neutral axis. So then we know that the relation between arc length, radius and angle subtended. So arc is equal to radius into angle subtended. Therefore, A dash B dash O arc length which is equal to R plus Z, the radius of curvature for the layer at a distance Z from the neutral axis and theta angle subtended. The original length, so called AB neutral axis for neutral axis, where R is the radius with respect to neutral axis, theta angle subtended. AB is equal to R theta. Therefore, increasing length which is equal to A dash B dash minus AB. So, because initially all the layers they have same length, when we applied a load at both the ends of the rod or beam, one of the layer which neither elongated nor compressed so-called neutral axis, where the layer which exists above that neutral layer or surface so get elongated. Then the increasing length which is equal to A dash B dash minus AB, then substituting the values A dash B dash and AB from the above equations, then we will get R plus Z into theta minus R theta. Then after simplification, say R plus Z theta is, which can be written as R theta plus Z theta minus R theta, where R theta get cancel each other. Then increasing length which is equal to Z into theta, let this is equation number 1. So by the basic definition we know that strain is equal to change in length by original length. Then strain is which is equal to a change in length Z theta, original length R theta, where theta get cancel each other. Then further which is equal to Z by R, let this is equation number 2. Hence, the strain is proportional to the distance from the neutral axis. That means as we move from the neutral surface or neutral axis, then the strain goes on increases. Now consider a small area delta A at a distance z from the neutral axis. So then by the basic definition, we know that Young's modulus which is equal to stress by strain. Then further which can be written as stress is equal to y into strain. That means stress is equal to Young's modulus to strain. By the basic definition, we know that where stress is nothing but force per unit area, then F by delta A, which is equal to Y into Z by R, where F by delta A that gives stress, Z by R that gives strain. Then the force on the area delta A, which is equal to Y into Z by R, that means on the area delta A, so called F is equal to Y into Z by R into delta A. Let this is equation number 3. Then moment of force, by the basic definition we know that moment of force, which is the product of force into perpendicular distance, so that the moment of this force, which is equal to force into distance, from the equation 3, the force Y into Z by R into delta A into Z, where perpendicular distance, so called Y into Z by R into delta A, that gives the force on the area delta A, where distance Z, the distance between the selected surface from the neutral surface. Then after simplification, we will get moment of force, which is equal to Y into Z square by R into delta A. Let this is equation number 4. So then the total moment of forces acting on all the filament is given by the summation of the above equation 4. That means sigma y delta A Z square by R, which is equal to Z by R sigma delta A into Z square. So look here, where sigma y delta A Z square by R, which is equal to Y by R sigma delta A into Z square, where Y by R, where Y is Young's modulus, R radius of curvature, both they are the constants. But as we move from the neutral surface, both the area of cross section of the layers and the distance of the layers from the neutral axis of neutral surfaces goes on changes. So the area of cross section goes on decreases from the neutral surface, whereas the distance of the layers from the neutral surface goes on increases. Here sigma delta A Z square is called the geometrical moment of inertia Ig of the section. So that geometrical moment of inertia Ig, which is equal to sigma delta A Z square, which is equal to A K square, where A area of cross section of the beam, K a radius of gyration. Let this is equation number 6, where A is the area of the surface and K is the radius of gyration. Then moment of force, which is equal to Y by R into A K square, force into perpendicular distance. Then substituting sigma delta A Z square is equal to A K square in the equation 5. Then we will get the moment of force, which is equal to Y by R into A K square, which is equal to Y by R into Ig. Let this is equation number 7. This is called the restoring couple or the bending momentum of the beam. So M is equal to bending, usually the bending moment, which can be represented by the letter capital M. M is equal to Y by R into Ig. Let this is equation number 8. Y Young's modulus of the material or radius of gyration. Ig geometrical moment of inertia. Here the quantity y Ig is equal to y into AK square is called the flexural rigidity of the beam. For rectangular cross section, if suppose the beam, if it is a rectangular cross section, then A is equal to B into D, where B is the breadth of the beam and D thickness of the beam. For rectangular cross section, the radius variation which is given by k square is equal to d square by 12. Then substituting the values a and k square in the above equation, so then we will get Ij is equal to a k square which is equal to bd into d square by 12 then bdq by 12. Then where the Ig in the equation 8 is replaced by bdq by 12, then the equation 8 becomes. So bending moment for rectangular cross section m is equal to y b dq by 12 r. Now this is equation number 9. So for circular cross section, a is equal to pi r square and k square is equal to r square by 4. So then the bending moment m is equal to y pi r square r to the power of 4 by 4r. Let this is equation number 10. Then where r is the radius of cylindrical or circular cross section, then where radius of gyres in k square is equal to r square by 4 and area of cross section E is equal to pi r square. So then Ig is equal to pi r to the power of 4 by 4, where Ig in the equation 8 which can be replaced by pi r to the power of 4 by 4. Then finally we will get m is equal to y pi r to the power of 4 by 4r. Let this is equation number 10. From the above equation, it is clear that the bending moment is directly proportional to the Young's modulus of the beam. If you see the equations 9 and 10, so then we concluded that the bending moment of the beam is directly proportional to Young's modulus of the Young's modulus of the beam. By substituting the values of Young's modulus y, then pi, then r radius of the circular cross section, then r radius of curvature, then we determine the bending moment of the beam. So then now you come to the point cantilever. What is cantilever? Then what about the theory of the cantilever? A beam fixed horizontally at one end and loaded at the other end is called cantilever. Now you can see AB is the beam, where A is the free end of the beam and A is the fixed end of the beam and B is the free end of the beam. Let L be the original length of the beam. If you applied a load at the free end of the beam B, where the beam which free end of the beam which shifted from the point B to B dash. So let us consider any one of the arbitrary point P which is at a distance x from the fixed end and L minus x from the free end. Then we draw the tangent from the R before that. Consider a arc of the, that means a small portion of the cantilever PQ, where PQ is nothing but arc of the circle. When you draw the radius of curvature from the points P and Q, then they will meet at point O, where R is the radius of curvature, d theta angle subtended. Then a dx, say the length of the arc. If you draw the tangent from the points P and Q, both they will meet at point C and D. where dy that gives the depression from point P to Q. So this is what about the diagram of the cantilever. Let AB be the natural axis of the cantilever of length L as shown in the figure. It is fixed at end and loaded at B with a weight W. Then the end B is depressed into the position B and the natural axis takes up the position AB dash. Consider a section P of the beam at a distance x from the fixed end A. Then the bending moment. By the basic definition, we know that force into perpendicular distance, so called W, that gives W is equal to mg, so called force, that means into PB dash perpendicular distance, then which is equal to W into L minus X. So since the beam is in equilibrium condition, then we can write W into L minus X, which is equal to Yig by R, which is equal to YAK square by R, where Ig is equal to AK square, so that W into L minus X, which is equal to YAK square by R. Let this is equation number 1, where R is the radius of curvature. Then for the point Q, which is at a distance dx from point P, then we have PQ is equal to R into d theta. So from the relation between the arc and radius and angle subtended, based on that, PQ is equal to R into d theta. Similarly, dx is equal to R into d theta. Therefore, R is equal to dx by d theta. Then equation 1 becomes W into L minus X, which is equal to YAK square d theta by dx, where R which can be replaced by d theta by dx. Then d theta, which is equal to W into L minus X into dx by YAK square. Let this is equation number 2. Then the depression of Q below P, which is equal to CD, so called dy is equal to L minus X into d theta. That gives the depression. Then dy is equal to W into L minus X into 2 into dx by YAK square. Let this is equation number 3, where dy is equal to W into L minus X whole square into dx by YAK square. Let this is equation number 3. Then the total depression of the cantilever, which can be determined by the integration method. Then the integrating the equation number 3, then we will get y is equal to integration of dy with the limit 0 to L, which is equal to integration of W into L minus X whole square into dx by YAK square with the limit 0 to L. So further, which can be written as, which is equal to W by YAK square integration of L square minus 2LX plus X square into dx with the limit 0 to L. Then W by YAK square. Then applying upper limit and then the lower limit. Then we will get. So the integration of L square minus 2LX plus X square into dx, which becomes where L square X minus 2L, where X is there. So after integration, X square by 2. Here X square is there. After integration, X cube by 3. So W by YAK square into L square X minus 2L X square by 2 plus X cube by 3. So then here 2 get cancelled, and then applying lower limit and then the upper limit. Then after applying the lower limit and upper limit, then we will get, which is equal to then total depression, which is equal to W by YAK square into L cube minus L cube plus L cube by 3. Here plus L cube minus L cube, they get cancel each other. Then we will get y is equal to W L cube by 3y a k square. So y is equal to W L cube by 3y a k square. Where a k square, a is the area of cross section of the surface, k radius of gyration, that is equal to Ig. So where Ig is known as geometrical moment of inertia. Where y Young's modulus of the materials, then here the small y depression, where W weight or the load attached at the free end of the cantilever. So got W is equal to mg. Then where W which can be replaced by mg, where a k square which can be replaced by Ig, then we will get y is equal to mg L cube by 3y Ig. So this is the expression for Young's modulus, where Young's modulus y is equal to mg L cube by 3y Ig, where m mass in the scale pan, j acceleration due to gravity, so called 9.8 meter per second square, L original length of the beam or cantilever. So here small y, that gives the depression. Then Ig, geometrical moment of inertia. So this is the expression for Young's modulus of the material. So if suppose the bar or beam or cantilever, if it is a rectangular shape, then the radius of the um, geometrical moment of inertia a k square, which is equal to b dq by 12, then where a k square in the above equation replaced by b dq by 12, then the above equation becomes, so Young's modulus y is equal to 4 mg L cube by yb b dq. If suppose the bar, if it is a circular cross section or a cylindrical cross section, then the geometrical moment of inertia a k square, which is equal to pi r to the power of 4 by 4, where r radius of the cylinder, then substituting in the above equation, then we will get y is equal to 4 mg L cube by 3y pi r to the power of 4. So this is the expression for Young's modulus of the cantilever or beam if it is in the circular cross section or cylindrical form. Thank you.